Next is Michael Keester. He's with LRE Water as investigating the potential for subsidence due to groundwater pumping with application to joint planning.
So thank you very much for the opportunity to come here and share the study that we started back last year in 2017. We worked on this project in order to, on behalf of the Water Development Board, to develop a better understanding of what is the potential in these major and minor aquifers for subsidence due to pumping, and that was really the goal of the project. I want to first of all thank some of the folks that we worked with there. The Water Development Board, of course, they funded this project. We appreciate them choosing us to do the work. And we also worked with Blanton and Associates. I know Velma reached out to many of you and appreciate the help that you provided us with providing data and information on what was happening in your districts. We also worked with Wet Rock Geoscience and GLS Solutions to help. They helped us with describing some of the aquifers and developing that understanding there. So I want to talk a little bit about what some of the project objectives were. We're going to look at the methods that we applied to assess aquifer subsidence risk. Just give you a little summary of that evaluation, and then turn more towards how this can be applied towards the assessing desired future conditions and what those proposed DFCs the impact of them on potential subsidence, and then give you a few ideas on some potential management, ways of managing subsidence risk. So as you know, you're required, some of the requirements within the Water Code are that you look at subsidence and with relation to your management plans, to permitting, and to assessing desired future conditions. However, for the most part, you just didn't have the data, didn't have the tools to really provide a meaningful assessment of what that subsidence risk would be in those contexts. So that was really one of the main objectives of this study, was to develop that information for the Water Development Board and that you'd be able to use there. As you know, even you look at some GCDs in the management plans and it says that it just simply isn't applicable within the district. Well, you now have something kind of to hang your hat on with regards to that. So two things that came out of the project were the report describing the work and describing the results, and then also a tool that you'll be able to use to provide a little more information when you have to answer that question. So looking at the methodology, as you know, Texas has a lot of aquifers, 21 minor aquifers, 9 major aquifers, and the lithology of these aquifers is not the same everywhere. So for this level of a study, we were looking at this high-level analysis. We wanted to develop a means, a way of applying a consistent method across all of the aquifers in the state. So we had to try to consider all the different lithologies, the different changes in water levels, looking at how deep have the water levels been in the past and how could that have an effect on potential subsidence, and roll all of this information together. We presented our methods to the Water Development Board. We got some feedback. We changed some ideas there, and then kind of rolled with this to present one method for assessing all of the aquifers. Now, one of the most important things is to look at how much clay is in the aquifer. It's very important for determining the subsidence risk. In order to look at this, we turned to the Submitted Drillers Report database. It's a text file database. We had about 350,000 wells that we were able to look at, providing this statewide coverage. Looking at across the state, it was that one data source that we were able to turn to. Gave us the advantage of it being pretty easily automated. We're able to take this, run some scripts, let the computers figure out some different information in there. And it was also going to be something that could then be repeatable in the future. So it was good for this project, and then it could also continue to be used as that database expands. And while we would love to have been able to spend the time doing geophysical log analysis, it just really wasn't practical to look at the entire state and all of the geophysical logs available. Well, one of the things that came out of it is that we found, as you might expect, there are a lot of different ways that a driller can describe clay. You've got the nice general, clay, that's nice and easy. Of course, you've got black land, you've got shale. We ran into things like gumbo, sticky. That's one of the descriptions that we had to start looking for in these descriptions. And as you also might imagine, there's a lot of different ways they can spell these terms. So we had to try to set up these tools in order to figure out, okay, looking through this, how do we figure out how much clay and how much clay they're describing is in there? Well, we also had to address where clay may be described with something else. For example, you may see silt and clay, rock and clay, caliche and clay, clay and sand, for example. So we had to come up with some way of going, okay, we have all these different ways to describe clay, all these different modifiers on what's within an interval. And so to address this on a statewide basis, we ended up applying just multipliers when we saw some of these modifier terms in there. So for example, with sand, we would look at the sand and go, okay, well, we're going to have to assume, without any better information, that about half of that's clay, half of that is sand. So for an example like this, for this interval, we'd be looking at 40 feet of sand, multiply that by 0.5, assume 20 feet of clay within that interval. So that was the starting point. We also had to figure out, well, we have this clay, but how easy is it for that clay to compact or squish, the compressibility of that clay? It's an extremely important consideration for subsidence, but it's not typically very well known. We don't usually have a lot of measurements of it, especially for these deeper aquifers. So in that case, we had to look at the aquifer as a whole, do some research on descriptions of the aquifer and the lithologies of the aquifer, and assign one of three classes essentially to that clay. Is it a plastic clay? Is it a stiff clay? Or is it a hard clay? And then we would apply that range of compressibility values to it. So another important consideration, of course, is how are water levels changing? What have they been in the past? What are they expected to be in the future? And that's going to have a big impact on what the potential for subsidence there is. For the pre-consolidation level, or an estimate of that deepest water level in the past, we looked at the transient calibration portion of the GAM. Not perfect, but it provides us, once again, that statewide coverage for the most part of what water levels might have been at these well locations. For the future water levels, we looked at those DFCs and the MAG simulations in order to get a better idea of, well, what's the water level going to do in the future? How much is it going to decline? How much it may arise? And then we also looked at, well, what's the trend in water levels? We would look at what was using typically about a 20-year period there towards the end of that calibration run. How were the water levels trending? Irrespective of what the estimated predictions are for the DFCs, how had they been trending in the past and where would they be projected to be in the future? We did, of course, have some aquifers that did not have GAM, or at least one that was going to be really reasonable to use for these predictions, in which case we would we turned towards those measured water levels. And we would use these as well to help inform our information. This is an example of a well out there in the Wécomisil-Bossons, where the models didn't really give us enough information to maybe make those predictions or those DFC determinations as to what the future water level would be. So we use this trend in order to get an idea of what's the water level in the future and how could that potentially affect the potential for subsidence. We came up with, taking all of this information, we brought everything together and looked at different class values. We classified the different risk factors and developed a risk value for each well that we did an analysis for. A little over 350,000 wells that we were able to develop this risk assessment for. Assigned those to the aquifers and the layers within the aquifers and some of these multi-layered aquifers. Took this information, just simply calculated some statistics And then broke that down into just three kind of simple classes of high risk, medium risk, low risk. So just to try to keep it as simple as possible. The results ended up being 7 aquifers were identified as having a high risk for potential subsidence. 5 of those being the major aquifers, the Ogallala, Carrizo-Wilcox, Gulf Coast, as we anticipated, the Waco-Mesilla-Bolsons, and the Pecos Valley. And then the 2 minor aquifers, the A.Y. Jackson and the Brazos River alluvium. The thing that is in common with these aquifers is they all are essentially unconsolidated clastic aquifers, that is, they're sand and gravels and clays, and they have relatively thick clay sections within those aquifers. So I'm going to turn now and look at just a couple of specific examples as to how these evaluations played out. Turn to the obvious one first, the Gulf Coast Aquifer. That one, we came up with a risk value of 5.9. It's a number that it's kind of a qualitative assignment of those different weights and those different values in order to come up with these quantitative values. But that 5.9 shows that aquifer, as you can see from the multitude of red and orange colors there, there's a lot of wells showing a relatively high risk for subsidence. The clay thicknesses are typically fairly thick. It has clay that's pretty squishy, for lack of a better term, and so as we would expect, we have a subsidence there. But we can take this information here, and this is where it may become is going to become a little more applicable to the districts and to the GMAs, but we can zoom in. So let's say we look at GMA 15 in particular. In GMA 15, we see that one of the things that we see immediately is that value, it goes up to a 6.7. So it's suggesting that there's a higher risk for potential subsidence within GMA 15 than there is in the Gulf Coast Aquifer as a whole. The key factor there is that in general, the average or the third quartile anyway of the clay thicknesses are typically much thicker within GMA 15 as opposed to the entire Gulf Coast Aquifer system. So this gives you that next level of information when you start to zoom in, you start to look at these specific areas in order to give you that better idea of what the potential subsidence risk is. Now, if we look at another big aquifer out there in the Ogallala, for example, lots of production out there. That's one of the ones that was identified as also having a higher risk due to the thicknesses of the clays, the potential declines in water levels that are anticipated. So those are some of the factors that really weighed in to raise this Ogallala up to the level of a potentially high risk for potential subsidence. And there's another situation where we can zoom in and we look at the High Plains District, for example. And here we see also, just like we saw in GMA 15, there's a slightly greater risk. Now this risk here, the change is not due to clay thicknesses really being that much different, but here it's due to water levels. The trend in the water levels based on past measurements, it shows a little bit greater decline of about 68 feet over 50 years as opposed to 45 feet that was for the Ogallala as a whole. So that's where we can see where some of these different factors can start to play in and change the risk, change the assessment of that potential risk. But for each aquifer, as I mentioned, we developed this information. We developed all of this information on a well-by-well basis. So that's what gives us this opportunity to take the information, and look at it at essentially any geographic scale, so on the county, on the GCD, and the GMA, on the aquifer as a whole, as well as looking at it for the various layers of aquifers. So for example, within the Carrizo-Wilcox, we can look at the Carrizo as well as the upper, middle, and lower Wilcox, depending upon where that well is screened and producing from. But to extend these results so that to give you something a little bit more than just a risk factor that you can understand and have an idea of for the management plan and for the DFCs, we extended it and worked with the Water Development Board to develop this subsidence prediction tool. that you'll be able to use. The tool itself, it uses the same calculations, the formulas are the same as you'll find in a ModFlow subsidence package. So no change there from some familiar tools that are out there. It does give you that opportunity to put in those site-specific information, though. Now, one of the caveats with the tool is that, and you'll see this shortly, is it does not include the time delay component of subsidence. Now, what that means is that it's going to calculate what the potential subsidence would be as if it happened immediately with that change in water level. So it doesn't include that portion of it. And that's why we, in the Water Development Board, we consider this a screening level analysis and a tool to give you an idea of what the potential is out there. And one of the goals was really to make this thing just really as simple as possible, make it so that it's going to be as user-friendly as possible. I'm going to run you through a couple of examples here real quick, and just like I think was mentioned yesterday, I'm not going to do a live demo because I don't want the computers to crash. So I'm just going to show you a few screenshots, but if you have any questions about it, feel free to catch me later, I guess, about it. Or when you first open the tool, for example, the first thing that's going to pop up is this nice blank screen that has no inputs in there and doesn't really tell you a whole lot other than it needs some information in order to move forward. So the first thing you're going to want to do is select what aquifer you're working in. Now, let's say, for example, you're working out there in the Carrizo-Wilcox, and you select the Carrizo-Wilcox aquifer. All of a sudden, you'll see that everything gets populated with those default values for the Carrizo-Wilcox aquifer. So all of the values that then get populated into these different fields within the tool are based on the results of the study. It fills it in with those average values that were calculated for each of the aquifers, just really to kind of give you that starting point. The gray boxes in there, they're going to give you that options to change some of the default values. You can select, for example, if you think for the Carrizo-Wilcox, instead of being a hard clay, it should be something different, you can change that. And it's going to change all of the calculations within there in order to make it more appropriate for what you're looking at. And also, since the tool is designed to kind of give you that blank slate each time you open it, you do have that option to kind of turn that feature off so that you can save this thing for, say, you're looking at a potential DFC or a potential effect at a well site. You're able to take a look and make several copies and save copies of this, save your work. And one of the results that you will get from this is just a simple chart. It's going to give you, based on the minimum and maximum compressibility of the clay that you've selected or is defaulted in there, of what that potential subsidence is with that change in water levels. So you get this range of values of what that potential is. Once again, just remembering that there will be, it's a looking forward without considering how long it might take for that subsidence to occur. So let's look at a specific example. Let's go back into High Plains District over there. The Water Development Board, they have one of their recorder wells out there. That's in Lamb County. And current water level out there is about 149 feet below ground level. Clay thickness in there, well, how will we calculate that? We can go and look at the lithology that they have, and we see that there's clay described at 8 different locations within that lithology table. Every one of those has some kind of modifier with it. In this case, they're all pretty much sand. So we can take that information, let me go back real quick, we add that up, it's about 120 feet. We use that multiplier, breaks it down to 60 feet of clay within the wellbore. But then we just have to look at, well, what's the saturated? How much clay is actually underwater? How much of it could actually be potentially drained? And that's where we drop that value down to, it comes down to about 20 feet of clay thickness there. So we can take this information, and with it, we open up the subsidence prediction tool. We look at, it's populated with those default values for the Ogallala, and let's start changing some things. We're going to put in what's the water level there. change where the land surface is, change the top of the aquifer. Add that information in there for each one of these parameters. And with these first few changes, what we see is just, all it changes, it doesn't change the risk, but it does change the specific storage values, which will have an effect on how water levels are calculated and how those predicted water levels are changed. So it's important to change those as well. But then we go in and we also change, well, we have a, excuse me, we need to update the pre-development water level, update what the current water level is, change the saturated thickness out there, so how much is unsaturated, and change the different predicted water levels as well. And we see then that the risk actually goes up because of this change in water levels that we put in there and these different values. So it goes up just slightly. But one of the other things in there that then we're looking at, for the Ogallala as a whole, the predicted change in water level is about 0.86 feet per year. Well, when we look at this well in particular, and we calculate the trend based on those water levels that have been observed, that level goes up to 2.7 or 2.27. And now we see a significant increase in the subsidence risk associated with that well. It becomes more of up to a value of the 5.8 for the risk value. So this gives you an example of how you can take information from a particular well, bring that information in, and then you can see what the estimated subsidence risk value is compared to the aquifer as a whole. But let's say you also want to change, this is where you can change back and say, well, instead of, let's change the clay type into a clay that's not quite as compressive. And you can see where that has an effect as well as far as dropping that subsidence risk value back down. So this just gives you that particular application. And you can put in this information as far as either on a well-by-well basis. You can look at it on average conditions for a DFC, for example. And let's say you're looking at the DFC results. This is where you could look at, well, what's the change from the DFC versus what's going on at that well? If we look at the Ogallala mag run, over there on the right, we see that, well, that range in predicted subsidence goes in essentially from 0.02 or 200ths to 300ths of a foot. And at the well, it's still less than 1/10 of a foot. Or what's this letting us know is that, okay, the conditions are right, the lithology is right, the water level changes are right to show that there is a risk for subsidence, but that magnitude is not going to be very big. So this is where you can start looking at these different factors and go, okay, even though there's the risk, the magnitude is not going to be significant enough for us to be concerned about what's going on here. So this gives you those tools that you can start to develop into your management plans and into the DFCs to start looking at. But what if you are in an area where you see some risk? Well, that's where management is going to come into play. Monitoring methods, as I'm sure you're aware of, we have extensometers in the Gulf Coast Aquifer. There's one that used to be out there by El Paso that was measuring changes in land and subsidence out there. We use GPS. That's a very efficient way of looking at potential changes in land surface, as well as benchmark releveling. But one drawback of these different methods is that they provide that information at specific locations. So you need to get a lot of them together in order to get a better idea of what's going on kind of spatially. However, they can still miss maybe an area where subsidence is significant and is occurring. So there's a relatively recent method that's being developed using some satellite data. It's the name that I will mess up, I'm sure. It's interferometric synthetic aperture radar, and that's why everybody calls it INSAR for short. A whole lot easier to say. But it gives you that information where they can measure changes in land surface down to the half-inch scale over large areas of land. Comparing the information from as the satellite passes every couple of weeks, I think it's every 6 to 20 days approximately that you can get a measurement. And you can start to look at those comparisons and get an idea of where is the ground changing. This is an example out there in California. It's actually just north of where I grew up, where you see the land surface changes from the satellite data. And the area that is experiencing the most subsidence, that bright red spot up there, actually doesn't have any monitoring right around it. So you wouldn't know it was occurring if you didn't see it here in the satellite imagery. So it gives you that additional way of looking at it. And the same method has actually been applied here in Texas over there. It's one area it's been applied over by the USGS along the Gulf Coast in the Houston area. It's also been applied over by the Wink Sinks area out in West Texas, where we can see that we have the two, Sink 1 and Sink 2 over there, but then to the east of that, we see a large area of deformation that's occurring. So with that, just a quick summary. One of the things that really we took away from it is that subsidence risk, it's not isolated to the Gulf Coast aquifer. That risk can occur within many of these aquifers across the state. The lithology and the water level changes suggest that it could occur. This developed a lot of valuable information, we believe, for the Water Development Board, for the districts, for the GMAs, to meet those statutory requirements. And that tool is really going to provide a means for giving some kind of quantification to addressing the requirements, the water code there. One of the key things, if you are looking at management, monitoring is going to be the key to that effective management. Basically, looking at ways to effectively monitor what changes may be occurring. That's going to be a necessary part of this. So with that, turn it back to Greg.